Let's make a start. So, hi everyone. Thank you for coming to my talk today. I'm going to be talking to you about ARM64's weakly ordered memory model and the need for correct and minimally intrusive barriers. I have quite a lot of material to go through. I'm not quite sure how much we will actually get through in the 30 minutes, so we'll see where we can get. If people are interested in staying a little bit longer, I'll stay around and I'll keep presenting through if we've not actually made it to the end, but we'll see. So let me just figure out how to use this software. So do I click and that'll work, or do I have to press that? Okay, there we go. So firstly, who am I? So my name is Ash Wilding. I'm part of the Amazon Web Services EC2 kernel and operating system organization based in Cambridge. Before this, I was actually a senior engineering manager back at ARM, where I was a team lead of the architecture and open source software support organization. So my background is in helping engineering teams to design architecturally compliant hardware systems, develop architecturally compliant system software components, and also apply certain open source software components on ARM-based hardware platforms. So things like TFA, Linux kernel, and the team will at some point be doing Zen as well. Obviously, there's ARM interaction with Zen now, with people like Bertrand and Rahul on the call. So why this topic? This isn't really a Zen specific topic, but it's one that I think can be quite interesting. Barriers are one of the biggest stumbling blocks that people face when they're building ARM-based systems. That are both new and experienced engineers alike. And these barriers are sometimes seen as being scary. You know, people have a tendency to use stricter and more intrusive barriers than are actually necessary just to be safe. That has performance implications, but it can also actually hide more sinister underlying bugs. You could actually have a bug in either your software or your hardware that lays dormant for many years and just doesn't happen to be exercised. And then when you move to a newer revision, either of your software or a newer revision of the hardware, suddenly that bug actually manifests. And those can be very tricky to try and debug because all of your assumptions around, well, I've had this known good working system for X amount of time, something must have changed. Actually, the supposedly known good system was subtly broken and just never manifested. And this means that choosing the most relaxed and minimally intrusive barrier that still guarantees correct behavior is a useful skill. We're starting to see more and more involvement of the ARM architecture in various projects, and a lot of people come from a background that may be more strongly ordered, people who have mostly worked, for example, with the x86 architecture. So I'm hoping that this talk will be interesting, whether you're new to the ARM architecture or not, maybe highlight some of the potential pitfalls and things that you need to keep in mind when working with a weakly ordered memory model. So ARM's weakly ordered memory model, what does that actually mean? In the simplest terms, there is no requirement for non-dependent loads and stores to normal memory in program order to be observed by the memory system in that same order. That's quite a mouthful, so let's just break it down a little bit. When we talk about non-dependent loads or stores, there are two different things we can talk about. Now, I've got some assembly on the screen. I appreciate the fact that a lot of people on the call may have never seen assembly before, especially they may not have seen ARM assembly before. Don't worry, things are going to be kept really, really simple, and I'll explain things where they're needed, but for the most part, you don't need to know what the code is actually doing. Okay. Now, the code you can see on the screen here, it's two loads. And the way that you read this is the x1 being in the brackets. You can think of that almost as like being dereferencing a pointer. So what we're saying here is load the value at the address held in x1 into the register x0. But you can see that the second load computes an address from the value that we just loaded from x0. So it takes that x0, adds 4 to it, and that's forms the address that we then load to into x2. Now, these are what we call an address dependency, right? Oh, sorry, a register dependency. That's because the second load depends on the first load, which means that these loads cannot be reordered with respect to one another. Okay, so these are dependent. You don't have to worry here. That's going to be automatically resolved by the CPU, and you don't have to worry about reordering. Similarly, I'm going to have here a store. Now, I've tried to turn this into a bit of a colorful picture to indicate what's happening. So this is a 64-bit store, or 8 bytes. And so each of those little colored squares in blue represents 1 byte of the 8 bytes that are written by that store. Okay. Now, if I have another 2 stores after here, you don't have to worry about the actual assembly on the left. If you just look at the colored squares, the second store is a 2-byte store to where the yellow squares are, and the third store is a 4-byte store to where the orange squares are. Now, a few things to note here. So there are no register dependencies like what we were seeing on the previous slide. Okay, I've very specifically constructed this sequence to avoid any register dependencies. But what you'll notice is that both of the yellow and the orange stores overlap the blue store. So what it means is they must be observed after the blue store. However, they themselves, the yellow and the orange stores, do not overlap. And they can be reordered with respect to one another. Okay? And we call that an address dependency. So an address dependency is where two loads or two stores or a load and a store overlap the same address, and that causes an address dependency and forces them to be observed in the same order. So here, again, the yellow and the orange can be reordered with respect to one another, but they both must be observed after the blue. I have another store here. This is a single byte store, and you can see it's overlapping the orange squares. So this green store must be observed after the orange store. However, it could be reordered to before the yellow store. So effectively, these two stores are a single block, and they're either going to both happen after the yellow, or they're both going to happen before the yellow here. They could even be ordered slightly separately, right? So I could even have orange here, then yellow, then green, so long as the green happens after the orange and the orange happens after the blue. So we get sort of complicated chains of dependencies here. If you think of it as colored squares overlapping and whether or not they're overlapping, you can very easily see where those dependencies are. So bringing that to a head, if I have a load here, this is an 8-byte load, and this 8-byte load exactly overlaps the entirety of those 8 squares that we've been talking about before. So it needs to observe the correct final value. So in here, it's going to see these two blues, these two oranges, this green, this is orange, and these two is yellow. And that's because that effectively makes it look as if all of those stores before happened in the correct order. So those are address dependencies. Now, other than these register dependencies and address dependencies, all bets are off. Those are the only two things that are actually going to cause a dependency between two different loads or stores. Okay. Other than that, you must assume that the CPU can and will reorder non-dependent accesses to normal memory. Normal memory being ARM's definition of where you have all of your code and your data. So it is basically DRAM, anything that's not MMIO. Vice, which is our word for MMIO, works a little bit differently. It actually has a reordering, non-reordering flag, but that probably does not work exactly how you may think it works intuitively. So we're going to come back to that example a bit later on. Now, I think the easiest way to think of this in terms of things actually being reordered is to think of a real example. So here we've got a pulled mailbox. Now there's quite a bit of information on the slide. I'm going to go through all of it right now, but it's there, and obviously the slides are available in PDF from the link that you'll have clicked to get to this this chat room. So take a look at the slides later if you want to see some of the more subtle details here. But the point is that we've got two CPUs. One CPU is going to be writing some data into a mailbox, and then it's going to set a flag to say, the data is ready. The other CPU, CPU1, is going to continually poll that flag until it is not equal to 0. And every time it's equal to 0, it's going to branch back and load the flag again. And that means that only once it reads that the flag is equal to 1 does it read the data from the mailbox, which is the final load down here. So whenever you have a situation like this, you're sharing data between different masters, you have to start to ask yourself, do I need a barrier? So if we were to think about this, between these two stores here, do I need a barrier? Well, what's going to happen if these two accesses are reordered with respect to one another? Well, that would mean that I would actually end up setting the flag before I've written the data. And that means that CPU1 would read potentially that the flag is set and read from the mailbox before the write to the mailbox had actually happened. So I think we need a barrier here. So then you ask yourself, well, actually, is there anything stopping these two things from being reordered with one another? Are there any register dependencies? Are there any address dependencies? Well, there are 4 completely different registers here, and you can see that X1 and X3, they're different addresses, right? So there's no register dependencies, no address dependencies, so they can be reordered with respect to one another, And that means I need something in here, a barrier, to stop those two accesses from being reordered. Okay. So am I done? Is that the only that I need? What else can go wrong here on this slide? We come down to CPU1's code sequence. You may be thinking, I don't need a barrier here, right? I'm going to keep polling that flag, and it's only when I see that the flag is equal to 1 that I'm actually going to read from the mailbox. And you may have heard some things around speculated values of down to speculated branch being discarded, but that only applies when you have dependent loads on the speculated path, and that we end up realizing that we speculated the wrong value and formed an address from that speculated value. In this case here, what you can see, that branch is doing nothing to stop the CPU from speculating past. Again, the only thing that's going to stop those things being reordered is if there's a register dependency or if there's an address dependency. So ask yourself, is there a register dependency here? No. Okay, you might think, well, they're both writing to W0, but that doesn't matter. That's not actually a register dependency. And there's definitely no address dependency either. So actually, I need a barrier here as well, just in case the processor either speculates past the branch or simply reorders the second load to before the first. Okay, so I'm talking about these barriers. We need this barrier. What actually is a barrier? Well, a barrier is an assembly instruction that enables software to manually enforce ordering. You basically tell the CPU, you are not allowed to do this until these conditions are met. So this is typically going to be required whenever you are sharing data between threads of execution, even concurrently on the same CPU, by the way. So even if you only ever have one thread executing at a time, single CPU, you're still going to need barriers. Okay, and we'll see why shortly. You also need to consider them whenever you're sharing data with other observers. So that could be other CPUs, but it could also be other bus masters, peripherals, and devices. We'll also need barriers whenever we're changing the configuration of the local CPU. So if I'm changing the system registers or if I'm changing the virtual memory layouts, things like this, those will also require barriers. Now, it's important to note that these things are not the same as compiler barriers. So those relate to sequence points during the code generation, right? They have no effect on the CPU pipeline because by the time your binary is an actual binary, right? All of those compiler barriers, they've already been resolved. It was just during the code generation step into actually generating your final binary. What we're talking about here are CPU pipeline effects, right? So you need explicit instructions in your instruction stream to actually affect that CPU pipeline. Natural follow-up question is, well, can the compiler insert these barriers for me automatically? And the answer to that is no. So C11 atomics, for example, they will use these barriers under the hood, but you still need to insert the C11 atomic in your code, right? The whole point is that the CPU and indeed the compiler, they don't have enough context around which accesses are actually dependent on each other, or contextually. So other than those register dependencies and address dependencies, it's not clever enough to infer that these two things are reliant. Okay, so that's what a barrier is. Here's an example of an actual barrier. So this is the data memory barrier, or DMB. So a DMB means that explicit data accesses before the DMB in program order must be observed before explicit data accesses after the DMB in program order. So we've got a little snippet of code on here. We've got an explicit store, we've got our DMB, we've got an add instruction, and we've got an LDR. Well, this add has no register dependencies with any of these loads and stores, and it's not an explicit data access, right? It's not a load, it's not a store, it's not a data cache maintenance operation like a data cache clean or a data cache invalidate. Therefore, this add can be reordered before the DMB, but the LDR cannot. Okay. So if we return to our example, where we had the big red barriers, you can see now, well, this is where we'd put our DMBs. So we would put our data memory barrier here. Now, that the qualifier, this allows us to restrict the effects of the barrier. Okay, and this is what I mean in the title of my talk when I say minimally intrusive barriers. Okay, you can put the most intrusive barrier you want here and you can get the correct behavior, but obviously there are going to be implications on performance. Okay, and in practice, what we want to do is use the minimally intrusive barrier that still guarantees the correct behavior on all implementations. So let's take a look at some of these qualifiers. So qualifiers allow us to limit the scope of the barrier, makes it less intrusive, reduces the impact on performance. There are two things we can do here. One of them is specify the group of observers to which the barrier applies. So this is a little bit of a tricky concept, and I could talk for a long time about it, so we've not got much time today, but I've got a little example of it on the right-hand side of the slide, and you can see the shareability domains there. Now, again, just to stress, this is an example. Okay, you don't have to have one inner shareable domain, one outer shareable, and one full system. You could have multiple inner shareables in your outer shareable, and you can have multiple outer shareables in your full system. But typically what we say is that a single inner shareable domain is usually a group of CPUs. And if you were running something like the Linux kernel, the CPUs that the Linux kernel runs in SMP across, that's your inner shareable domain. And actually, it's one of the requirements of Linux. Like if you go into booting requirements, you cannot boot Linux across multiple inner shareable domains, right? So an inner shareable domain is the group of CPUs that you can run in SMP. And you could imagine a big complex system that has multiple inner shareable domains. You might be running different operating systems there. You might have Linux kernel running on one, you might have an RTOS running on a different compute island, etc. So those would all be your inner shareable domains. Your outer shareable domain is a superset of that, so it'll contain one or more inner shareable domains, and that'll have the devices and peripherals pertinent to those CPUs as well. So we've got an example here of maybe a GPU, a DMA, and your GIC or some other IRQ generator. Okay. So by default, your barrier is going to apply to the whole system. But we can incrementally descope this using OSH to make it just the outer shareable domain, ISH to make it the inner shareable domain, or NSH if I'm saying this CPU, this mass, this observer, this is the only one that's ever going to use this data. Okay, so that's if you're just sharing between threads on the same CPU. In addition to that, we can also specify the access types that we care about. So it's going to default to no qualifier, and that means basically anything before the barrier must be observed before anything after the barrier. But I can use ST to mean I only care about stores before and stores after, or I can use LD to mean I only care about loads before or anything after. So coming back here again, if I put a DMB SY, that means full system, any to any. And that will work. That's good. But we can do better. Okay, again, this idea of descoping the barrier to make it minimally intrusive. So I could put it as OSH for outer shareable, and that's going to work. I can put it as ISH for inner shareable, and that's going to work. Can I go all the way down to non-shareable? Well, no, not in this example. Again, we've got two separate CPUs here which we're sharing that pulled mailbox between. And if you were to look into the details of the slide in the bottom right, I've mentioned that they're in the same inner shareable domain as each other. So this NSH won't work. Okay, so we do know that ISH is the minimal shareability domains that we can have for this. But I can still do better because I can see here that this is a store and this is a store for CPU 0, whereas it's a load and a load that we care about for CPU 1. So that means I can actually put this as an ish-st to mean inner shareable store, and down here I can put a DMB ish-ld to mean inner shareable load any. Okay, so these here are the minimally intrusive barriers that guarantee the correct behavior for the pulled mailbox example. Okay, so quick drink. I realize I've been speaking very fast for about 20 minutes. Hopefully I'm still making sense and I've not lost you. If you do have questions, please put them in the chat. I will do my best to answer them at the end, and I'll stay around again a little bit afterwards as well, and I can go through these things in more detail if people need. So let's start to look at some other real-world examples of using these barriers. Firstly, coherent DMA. So in this example here, instead of having another CPU, I've got some sort of DMA engine, which is going to be performing a DMA transfer. So this is a device, okay? Now, you'll actually see that the code sequence here for CPU 0 looks very similar to what we saw before. So I have my write to the DMA buffer and then a write to start the transfer, which looks very similar to writing to the mailbox and then writing to the flag, right? And so the exact same rules apply that we were thinking about earlier. Do I want these two things to be able to be reordered with respect to one another? Well, no, because I don't want the DMA engine to start transferring before I've actually written into the DMA buffer. Okay, can they be reordered with respect to one another? Yes, because there's no registered or address dependencies. Okay, so I'm going to need a barrier. Which barrier do I need? Well, I'll use my DMB like before, but instead of an ish-st, this time I'll need an osh-st, so an outer shareable store-to-store. And that's because the DMA is a device, so it's implicitly in that outer shareable domain. If you remember the example we saw earlier, the CPUs were in the inner shareable domain, and then those orange peripherals were in the outer shareable domain. So I do need to bump up my shareability domain here, and then this is the minimally intrusive barrier that guarantees correct behavior. Let's do a little slant on that example. So if I have a non-coherent DMA, okay, so non-coherent here means it's not cache coherent. So in that previous example, I didn't have to worry about the cacheability of the DMA buffer, right? Even if I had dirty data in my caches, what we're saying is that that DMA engine could snoop into my caches and take the dirty data. All cool. Non-coherent DMA is a little bit different because now I need to have my store like I did before. Okay, so the only thing that's actually changed in this code snippet is this DC here, this DC CVAC. Other than that, the code snippet is identical from the slide before. And what this DC CVAC does is it cleans that data out, the dirty data from my cache lines, out far enough into the memory system that the DMA engine can see it, which in this example here, that just means push it out to DRAM. Okay. So what we need to ask ourselves is, do I need a barrier between these two operations here? Well, firstly, let's ask myself, what would go wrong if they were reordered? Well, I would perform the data cache clean, which would clean out some of my cache lines. Then I would write to the DMA buffer, which would allocate dirty lines, right, into my cache. And so I don't want that, so I need a barrier, right? Actually, no. So this was a bit of a trick question. The reason here is coming back to that address dependency we spoke about earlier. Okay, so these are both what we call D-side accesses, right? We've got a data side store, which is the str instruction, and we've got a data side cache maintenance instruction, which is the DC. These are both data sides with an address dependency because they're both acting on X1, and that means I actually don't need a barrier between them. Okay, so what is this D side that I'm talking about? And this is where things might get a little bit trickier. So no ordering is enforced between accesses made by different observers, bearing in mind that an observer is anything that can generate loads or stores. An ARM CPU is not one observer, it's not one master, it's actually three, okay? And you can see that in this diagram we have on the left-hand side. So the D side is responsible for data side loads and stores and data cache maintenance operations. The I side is responsible for instruction fetches and instruction cache maintenance operations. And then we also have the TLB, or you'll sometimes see people call this the TLB side or the page table walker, etc. They're all referring to the same thing. And this is for doing page table walks and also translation look-aside buffer maintenance. Okay. Now, the fact that no ordering is enforced between these different observers comprising the same CPU means that we must take additional care when we're either modifying the page tables or if we're modifying program memory. Okay, and that's the example that we're going to go through now. So there's quite a few little instructions on here. I think it's always easier to sort of understand these by looking at pictures. So we've got the same diagram from earlier down here. Let's quickly step through the code, animated, and then we'll see which barriers we're going to need. So firstly, just to explain the situation, let's just say I've got an old opcode, okay? So some previous instructions in memory might be from a previous application I loaded. Maybe I'm loading in a new module, or maybe it's a JIT and I need to write a new opcode. There are different definitions of changing program memory, but all of those satisfy that, right? So I've got some old instructions, whatever they are, and let's just say that's the yellow star. This is in my iCache right now, which means if I was to branch into the code, I'm going to fetch that old instruction. I'm going to fetch that yellow star into my I side. I don't want that. Now, when I do the first store here, this is writing the new instruction that I actually want to be executing. That's going to cause a dirty cache line allocation, which is the green star, into my L1 D cache. Okay. which again means if I was to branch now into my code, this yellow star is still here, so I'm going to fetch the yellow star and I'm going to branch to the yellow star, which is not, start executing, which is not what I want to do. So I have two instructions here. The first one is a DCC val. Okay, so what this does is a data cache clean to point of unification. The point of unification being far enough out into the memory system that my D side, I side, and TLB side all see the same copy of memory. And you can see here in this example, the point of unification is the L2 cache, right? This L2 unified cache is going to be the point in the memory system where, for this particular CPU core, all three of those observers see the same copy of memory. So when I do the DCC val, I'm pushing that green star out into the L2 unified cache. When I do the IC val, that's an instruction cache invalidate to point of unification. So that's going to invalidate that opcode all the way up to the point of unification. So in this case, in other words, it nukes it out of the L1 I cache. Okay. And then finally, what that means is that if I was to branch now to the code, I'm going to miss in my L1 I cache, and I'm going to fetch that instruction from my L2 unified cache, and that's the correct opcode, and that's the code that I actually want to execute. Okay, so that's an explanation of what the code's doing. Now let's ask ourselves where the barriers are going to be needed. So firstly, we've got the store of the new instruction, and then I've got a data cache clean by virtual address to point of unification. So do I need a barrier between these two? Well, you might now remember from the previous example that these are both D-side accesses and they're to the same address. Therefore, I do not need a barrier, okay, between the store and the data cache clean. Do I need a barrier between here, between the data cache clean and the instruction cache invalidate? Well, let's first ask ourselves what might go wrong if these two things get reordered with respect to one another. So if my iCache started invalidating the yellow star, okay, the thing is that speculation, including speculative cache line fills, they can happen at any time for any or no reason, and you basically must assume that they're going to happen at the worst possible time. And for us, the worst possible time here would be that as soon as I've got rid of that yellow star from my L1 iCache, the L1 iCache immediately decides to speculatively fetch it again. And because our green star will still be in the L1 Dcache, okay, because the DCC val won't have finished yet, I'm actually going to refetch that yellow star that I just invalidated out of the L1 iCache. So that's not good, right? I need to make sure that before that ICI val even begins, that the L2 ucache has the correct data in the green star from when we were doing the step through, so that I know that the L1 iCache will fetch that instead, if in case it decides to speculate. Okay, fair enough. So I'm going to use my DMB, right? That's not going to be good enough. And the reason it's not going to be good enough is because if you remember what a DMB actually does, it's applying to explicit data accesses. And that does apply to explicit data cache maintenance operations as well. But we have an iCache instruction happening here, right? So the DMB has no effect. That means we need a new tool in our toolbox. Okay, so this is just showing that you can't have a DMB there because of the IC. So that new tool is a DSB, or a data synchronization barrier. It's very similar to a DMB, but it does things a little bit more stricter. So it actually prevents architectural execution of any later instructions. Doesn't matter if it's a data processing instruction or an actual data load or store. Anything after the DSB is not allowed to be architecturally executed until the things before it have completed. Okay. That obviously means it's considered very expensive because you're basically stalling the pipeline, right? So you should only use a DSB when you absolutely have to. Coming back to our example here, if I put a DSB-ish, that will actually enforce that the data cache clean is finished before the iCache invalidate even begins. Yeah, I see we're running up against the time already, so I'll try and finish this example. So that's going to ensure that that's finished. Now, next thing, do I need a barrier between my IC ival and my branch? Yes, I do, for the same reason that I was mentioning earlier, right? I don't want speculation to cause a speculative cache line fill and allow me to speculatively branch over into the old opcode, okay, that might still be there. So I'm going to need another DSB here to enforce completion of the iCache invalidate. So, am I done? Is that it? Is that all I need to do? I'm not done yet. There's something else that can go wrong in this sequence. Okay. Remember what a DSB does. I just said it prevents architectural execution. Okay. But that doesn't stop speculation from actually going past this point, okay, and already starting to fetch and decode stale instructions from the old context. So the DSB will actually ensure that the ICI vow has completed, okay, but we may have still actually fetched and decoded instructions from after that. And what we need to do here is actually tell the processor to abandon anything that it's done before, refetch it and redecode it, because now we've actually changed the contents of program memory. I need to make sure it actually gets that new opcode that's actually there. Okay, so this is another barrier. We can't put a DMB or a DSB here. It wouldn't make sense. So what I need is an ISB. Okay, so this ISB, or instruction synchronization barrier, it actually causes the processor to abandon all of its in-flight instructions, synchronize the context. So, any pending changes to the processor state are now visible. And then it refetches and redecodes those instructions that it just abandoned. So just in case we had speculated past the DSB and began fetching and decoding those instructions, remember, it wouldn't be allowed to architecturally retire them. Right, so that was the trick. The DSB prevents them from being architecturally retired, so it can't actually committed it, but we could have still fetched and decoded that old opcode, and that's the kicker. That's why I need that ISB and why the DSB isn't enough. Okay, so I think we're actually at the end of the time. Deb, how does this work? Are we able to carry on for a bit if people want to, or do I need to jump to a different room, or how does this work in a virtual setting? Are you there, Deb? You could.
Sorry, I posted in the chat. Design sessions are starting now, so we'll need to wrap this up so folks can head over to those. We have two, one in Shanghai and one in London.
So if this room is unused, can we carry on using this in case if people are interested?
There was a request to keep everything on schedule so that folks didn't miss other sessions.
I
I
guess
will
it
let
depends
folks
on
on the
whether
call.
people want to go there. Yeah.
Yeah, I'll let folks on the call decide, I guess, if they want to stay here or go to another. But since those two are the scheduled sessions and the request from the community was to stay on track, I want to make sure that option is out there. So it looks like folks want to stay. If you want to continue, this room can stay open.
Cool. Okay. Perfect. I'm glad people are interested as well. it's always a nice thing. So I mean, if we're turning this into an impromptu design session sort of thing, before I actually continue, does anyone have any questions? Because obviously I've been speaking at breakneck speed for about 30 minutes. Does anyone want me to recap anything before we continue, before we jump into some of the more interesting examples? Cool. Okay. So if anyone does have any questions as we go, just type them in the chat and I'll answer them as soon as I can. Okay. So we've now seen why we need the barriers that we do on here. You can see that quite a few. I think there's almost more barriers on here than actual instructions, which is quite funny. So coming back to an example we saw earlier, our polled mailbox where we said, can I need a DMB ISH-ST and a DMB ISH-LD as my minimally intrusive barriers here. Does that mean I can use a DSB here? Yeah, you could do that, but seriously, don't do that. The DMB is fine, and remember, the DSB is really, really bad for your performance. If you were really, really scared of your weakly ordered memory model, you could put a DSB after basically every single instruction, and it's going to work, right? You're not going to have any problems with the weakly ordered memory model, but your performance is going to tank. So, whenever you're using a DSB, you should really ask yourself, do I actually need a DSB here? right? And you might have a problem, you might have a bug where you can't quite figure it out, and you've got a DMB somewhere, and you replace the DMB with a DSB, and the problem goes away, right? And what you've probably done is masked the real issue, right? And you've made it go away, you've worked around it, but you've not actually resolved it. So whenever you're using a DSB, seriously ask yourself, like, am I doing something wrong, right? Is there a real good reason for why I'm using that? Question in the chat is, what is the performance impact? For example, the difference between using a DMB-ish ST and a DMB-ish. So this is having a DMB-ish, which applies to anything before and anything after versus store and stores after. It's really hard to say, right? It's very contextual. It's going to depend on your code, exactly what kind of data is being observed before and after, and which other observers you're sharing that data with, and the kinds and the patterns of accesses that your code is making. That probably sounds like a bit of a cop-out answer, but I mean the basic answer is you've got to profile it, right? But again, best practice is if you know that the reason you put this barrier in here is because I care about a store before and a store after, put the DMB-ish ST there, and you know you're going to be getting the best performance. It might be negligible, right? But you're also future-proofing yourself, because that might be that, especially as you start to go to bigger and bigger systems, right, where you might have hundreds of cores in the inner shareable domain. Do you really want every load and store before to have been observed by the entirety of those hundreds of cores before every access after the DMB, or would you not just want to restrict that down, right? So it's really going to be contextual on your system, your hardware system, your code, the access it's making, and so yeah, it is exactly. It's very, very hard to predict, which is why that again, the best policy is just try and to think and always use the minimally intrusive one, and then you're future proofing yourself regardless. Okay, so let's start to think about some slightly more interesting examples. So on the slide now, we've got a doorbell IRQ. So the idea here is that CPU 0 is going to do some stuff, maybe write to a mailbox, and instead of writing to a flag, which CPU 1 is polling over and over in a loop, we're actually just going to write to this peripheral. It might be like a doorbell peripheral or something, and that's going to cause an interrupt to CPU 1. And when CPU 1 takes that interrupt, it's going to read the mailbox, okay? So the code, again, looks really similar to what we saw before. And you'll notice this a lot, even if you don't have an explicit mailbox flag scenario, you quite often run into this same situation. So it could be, you're writing to some fields in a structure, and one of the fields in the structure is initialized equals true, right? Something like that. And other CPUs and stuff, it's not like they're polling for initialized equals true. It's not like they're going to be interrupted when initialized equals true, but they might want to do something like that. It might be a vCPU, right? So the real example that Julian and I were discussing several weeks ago, right? So another CPU might want to do something to this vCPU, but only if it's been initialized, right? And because if it's initialized, it can assume that the rest of the state is valid. And so you've not got that explicit sort of mailbox flag, but really, if you think about it from a more generic or abstract sense, you do. So this is yet another one, this doorbell IRQ. So I'm writing to my mailbox, I'm writing to my peripheral to cause an interrupt, and then over in CPU1, I'm in my interrupt handler, and I'm just going to do a load. So again, these two things, do I want them to be able to be reordered with respect to one another? Well, no, because I don't want to generate the doorbell IRQ before I've actually written the data to the mailbox. That wouldn't be good. So can they be reordered with respect to one another? Well, there's no address dependencies, no register dependencies. And something important to note here is that this first store to the mailbox, this is a write to normal memory, right? This is some buffer in DRAM. But this second store is a write to an MMIO write. This is a peripheral, and I'm writing to its register, and a side effect of writing to that register is that it's going to assert an IRQ. So this is actually mapped as device memory. And something to say straight away is that there are never any ordering requirements between normal and device memory. So to answer the question of can these be reordered, yes. And you might ask yourself, well, could I not do something where like I had an address dependency between the two? But if you had an address dependency between the two, you'd be aliasing the same piece of memory as both normal and device. And there are a whole bunch of caveats in the ARM architecture about what nastiness can happen when you do that. So yeah. So in this case here, I'm going to need a barrier, okay? Which barrier am I going to need? DMB HST. Okay. Now that may come as a surprise to you, depending on how astutely you've observed some of the things that I've been talking about. Because I said that when you map something as device, it's in the outer shareable domain implicitly. So don't I need a DMB OSHST here? And in fact, you saw the example earlier with the DMA buffer, right? The DMA engine. I had a DMB OSHST because I was doing stuff to the outer shareable domain. So why does that not apply here? Well, this is where we get that idea of the nested supersets of shareability domains. I actually don't care about the IRQ generator in the outer shareable domain observing the write to the mailbox before the write to the IRQ doorbell. It's actually worth noting the IRQ itself doesn't, the IRQ generator doesn't observe the write to its own register, right? So that's a completely different track of discussion that we could go down another time, but it doesn't observe a write to its own registers. What we actually care about here is that CPU1 has observed that write to the buffer, okay, to the write to the mailbox. And because CPU1 is in our inner shareable domain, and that's a subset of the wider outer shareable domain, which contains the IRQ generator, I can actually get away with an inner shareable ST here to make sure that the CPU1 has observed that store before it observes the write to the IRQ generator that then generates the IRQ. Okay. That's a bit weird, but now let's go slightly more complicated. So what have I got here? This looks slightly more scary. So I've got my cache coherent interconnect like before. Okay, and I might have a bunch of other stuff on this system that's not actually seen. Okay, obviously I've tried to minimize this just to make it fit on the slide. So I've got my cache coherent interconnect, and maybe I have some other interconnect hanging off that. Okay, so you could imagine you have your main compute complex where you have your high performance CPUs, big meshes working together, that your data plane, data processing and stuff. But many systems nowadays also have other, subsystems in the same SoC. So you might have a non-coherent interconnect hanging off there with some control plane things. In this case, maybe we've got a little microcontroller sitting on that non-coherent interconnect. Now, similar thing from before, I've got some buffer, some mailbox. In this case, it's going to be in the SRAM because it's a message that I want to share with the MCU. So it's down here. And I'm going to generate an IRQ again, just like before. Okay. So you might think here, maybe the only thing that's really changed is the fact that the MCU is now in the outer shareable domain. Okay, it's not going to be in my inner share. It's not like I can run Linux in SMP across these two things when the MCU isn't even cache coherent, right? So it's on this downstream interconnect. Maybe I can just use a DMB OSHST instead of an ISHST like we had on the previous slide. That's not going to be enough. Interesting. Why is that not going to be enough? Well, I'm going to need a DSB. And the reason is because of the fact that a DMB only enforces ordering between memory accesses that can actually be observed by the specified group of observers. If you look at the topology of this system again for a second, imagine the path taken by the write that's done by CPUs, right? Is going to come down this path here. I hope you can see where my mouse is on the slides, by the way. I can see a big red dot, so I hope that comes through. Yes, cool. Okay. So my write's going to come down here. It's going to go across the cache coherent interconnect, and it's going to go up into the IRQ generator. That means it never came down here, right? Everything that the MCU reads or writes are accesses that are flowing through this non-coherent interconnect. So if the access never gets to the downstream interconnect, it never observes it. And that means a DMB in this example isn't enough. The DMB does not enforce that MCU will have actually observed the write to the mailbox. Even if I did a DMB SY, right, which is full system, it doesn't matter because the MCU cannot observe that access. Okay, that means I need a DSB. Remember what the DSB does? It's basically stalling my pipeline, okay, until the observers observe it. So if I jump, remember the right, I need to go back, sorry, this way. Okay, so I need to do a DSB, and the reason I do the DSB is because what that guarantees is that the original store to the mailbox has completed. So by the time I get past this DSB, I know that data is down in SRAM. Okay. And by the way, this is I've mapped the buffer as non-cacheable, so I don't have to worry about any cache coherency stuff here, right? I don't have to clean it out to SRAM. I know that by the time I've done that DSB, it's sitting in SRAM, and then I can do my write to the IRQ generator, and I know that then the MCU will be able to read that data from the SRAM. Okay. So similar example then to that, but a little bit different for different reasons. This diagram is the same one we had earlier. If you remember when we were talking about the ARM CPU comprising different observers, so we had the D side, the TLB side, and the I side. I've just expanded it slightly to show two different ports that we have on this system. So the AXI slave port, that's pretty much the standard port that you're going to attach this CPU onto the bus with, right? So that's going to connect to your cache coherent interconnect, and maybe you've got some device sitting somewhere down in the system off that. Maybe this device here is a UART, for example. Maybe it's some sort of debug logging infrastructure, and when I do a write to this, it's sort of like a tracing and stuff. So just as an example. And over here, we've got something called an ACP, which is short for an accelerator coherency port. The idea of this is that you can attach a non-coherent master to the ACP, and it makes that master cache coherent. So you could take something like a non-coherent DMA, put it on the ACP, and all of its accesses go through the CPU's D side, which effectively makes it cache coherent because the D side is cache coherent. So it's a nice little trick. You can put some peripherals here that are specific to this CPU, very local to this CPU, and they're now cache coherent with that CPU. So similar sort of thing as before. Let's just say I'm going to do a write to device 0, and then I'm going to do a write to device number 1. So it might be, again, if this was some sort of debugging infrastructure, maybe, like I've got some very important that I can audit what's happening on this system. And if I write to device 0, it logs some message into some nicely ordered log. And maybe device 1 is a DMA, or it's going to start doing some copying, some transferring, right? And I need to make sure that when that timestamp is printed by device 0, that definitely happened before device 1 even started issuing any bush transactions, right? So I really want to make sure that this is observed first, this write is observed first. So thinking about what we've seen before, asking ourselves, would I be annoyed if these two things got reordered with respect to one another? Yes, I would. I've just been saying it's imperative that they are kept in order. Can they be reordered with respect to one another? Well, I've mapped these things as NR, right? Device ng NR. So that NR means non-reordering, right? So they can't be reordered with respect to one another. Well, let's just for a second say they can be reordered with respect to another, and we'll see why in a moment. Okay, so I do need a barrier. Which barrier do I need then? Okay, well, maybe I just need a DMB, right? Because they're both D-side accesses, they're both stores, they're both in the outer shareable domain, but it's actually the same as before. We need a DSB here, right? So the reason I need a DSB, though, is slightly different. Very, very similar, but slightly different to the example we just saw a minute ago with the MCU. So with devices, any two accesses that are either both to a non-reordering device type, so NR, or they're to any device type with a DMB between them, they're only actually required to be observed in order if they're to what the ARM architecture calls a single peripheral or block of memory that is of implementation defined size. That's typically confusing ARM architecture speak. What it really means in practice is that hazard checking only takes place per port. Okay, so in the example on the slide here, device 0 and device 1 are on separate ports, which means even if they're both NR type, there's no ordering enforced between them. And even if you put a DMB between them, there's no ordering between them because the DMB between two device types just makes it basically pretend as if they're both NR, right? So it's the same rules. And because it's not good enough for the NR type, it's not going to be good enough here either. And that means I need a DSB instead. Okay, so I've already gone 20 minutes over. So what I'll quickly do is show you something here, which I've sort of called a little take-home exercise. So you can see here that there's some code which is going to do a page table modification. Okay, so we have to do something in the ARM architecture called break before make. I won't explain why that is on the call. If you could take a look in the ARM and search for break before make, you'll find a little explanation as to why that is. Basically, what it means is I have to overwrite the translation table entry, the page table entry, with an invalid entry. It's like all zeros, for example. Then do the write of the what that I actually want to do, right? So I can't just modify a page table entry directly if I'm changing the mapping. There are certain conditions here where this applies, like if you're changing the address the output address, certain changes to the type and so on. I need to completely overwrite that entry first with all zeros to make it invalid, do a bunch of stuff, and then finally do my write of my new mapping, which is this final store here. And this sequence is that break before make. So before we even look at this, one of the things you'll notice straight away, I have data side accesses, I have TLB side accesses, which we've not seen yet, and I have iCache accesses, II side accesses. So that's all three observers of the same core. So this adds a little bit of complexity. I did say it's a take-home exercise, so here are some clues as to where you may or may not need the barriers. It's basically between every single instruction and at the end. And in the PDF deck that is available, again, linked on the page that you will have come to this talk from, you'll have access to this, which is upside down on here, but it's got the answer. But I would recommend having a bash at it yourself first. Hopefully you'll have picked up some of the little clues that I've been telling you throughout this presentation, and you would be able to get it and then compare your answer to what that answer is on the slide. And if you want to see more information about this, again, if you search for break before make in the ARM architecture manual, you'll actually find some good walkthroughs of it. There's also an entire appendix in the ARM architecture reference manual called the barrier litmus tests. If you're doing any sort of low-level development with ARM and you're going to be working with barriers, read through the entire barrier litmus tests appendix. It's very different to the rest of the ARM, right? If anyone's even tried to read the ARM before, you'll know it's not the kind of book that you would take to bed at night and read it in bed, right? It's very, very specifically written. It can be quite difficult to parse, but actually the barrier litmus test section is really nice to read through. It's got lots of really nice worked examples, and it does a nice teaching thing where it says, okay, we've got this problem, so I'll do these barriers. Actually, this is broken and this is why it's broken, and then it will give you the real solution, which is quite nice. So yeah, much recommended there. So that's the end of the material that I had for today. Hopefully that was interesting. Does anyone have any questions? Feel free to either type or unmute. Happy to stay for another few minutes, maybe till past, and answer any questions people might have. Bertrand's question is, any idea how much of the Zen code is currently wrong? I have no idea. I've not even begun to take a look at that. I know Julian has been doing some work at looking at various things, and some of the things he's been posting on the mailing list recently have been around sort of him spotting potential barrier issues. Yeah, it's tricky, especially one of the difficulties is when you have a code base that was originally and majoritively written for one architecture that doesn't have to worry about this a lot. Trying to find all of those little places where a barrier may have been, like a barrier on a weakly ordered memory model may have been missed, but nobody's noticed yet, and it all seems to be okay. And again, you can have real bugs in your code that are just not manifested on the hardware that you have available to you. And then finally you come along to a new hardware system, and one of two things happens, right? Either that hardware system is completely architecturally compliant, and actually there was a bug in your code, and finally that bug manifests on this new hardware platform, really easy in that situation to look back and think, well, we've got all of these platforms that it's always worked on, and it's just your new platform that's broken. Therefore, your new platform has a problem. And actually, no, it's a bug in the code. And the reverse is also true, right? You can have hardware platforms that are broken. Your code is fine and has been working fine for years, and then you come to a new revision of your hardware. You take the same piece of software on it, and now it's broken. And it's really easy to try and blame different things. So, yeah, it's a tricky problem. It's a big problem, and I think we'll see more and more of those manifest over time, especially as we see bigger and more complicated hardware systems using things like Zen. Question from Christopher is, could a CPU emulator, for example, QEMU, have a fuzz mode for stressing these barrier conditions? QEMU itself, maybe not. One of the problems with barriers is that timing matters, right? And anything which isn't timing accurate, you might not be able to manifest the issue. Now that said, there is a memory model explorer that ARM has developed. It's available on the ARM developer website. I forget the name of it now. There's this thing for the kernel as well. But it's basically about doing that, sort of being able to explore whether your memory model is behaving as you think it is, and whether you might be missing barriers. Disclaimer, I've never used it myself. I've just been pointed in its direction, so I know it exists and it's available there, but I don't know much about it. No problem. Hope you found it interesting. Any more questions? Thanks, Luca. Yeah, seeing if I can put a link into memory model tool. I think this is the one. DIY7, that's what I was trying to remember the name of. Yes, yeah, this is the link. This one here. Yeah, so I definitely have a read through that that page and have a look at the tool. It's supposed to be pretty good. Okay, cool. Yeah, thank you for the time today, everyone. Hope that was interesting. Hope you had some fun and learned something new. Take a look at the slides, and yeah, look forward to interacting with you on the mailing list. If you do have questions, feel free to poke me on the mailing list and stuff. If you spot anything in the in the Zen code base, especially around the ARM stuff, where you think, do I need a barrier here? Or you're looking at existing code and thinking this doesn't look right, please, ping me. Always happy to take a look. It's fun to sort of hash these problems out and see if we can come to the right conclusions. Thank you, everyone.